exactly. Okay. Yes. So I'm not, I study machine learning, but I'm not a specialist. I know nothing about reinforcement learning, also little about logic. And so I am a good person to speak at gentle level about these topics. My research, most of my papers are about like mathematical details about Kolmogorov complexity. So I should be able to deal with questions better than most people on this topic. Okay, so for connections with machine learning, in machine learning people care about classification, and classification is connected to sequential prediction. So in many statistical learning courses, they start with chapters on online prediction. Even my course starts like this. And so what is the problem? We receive a bunch of bits, x1 till xn, and we should try to think what is the next bit. So here is some examples, like the sequence in the middle. It's easy to think what is the next bit. But then there is a sequence in the top. Hopefully it's visible. Yes, it's visible. Here it's much harder to think what is next because I generate them with random coin in the beginning of the lecture. Okay, and in 1960, Solomonoff had an idea to define ideal strategy to solve this task. So imagine that the bits, they come from black box. We have no information. How can we continue this prediction? And so Solomonoff's idea was take a Turing machine that has no input but is random and let it print out bits one by one. Once a bit is printed, it cannot be changed anymore. And in this way, it produces a string. Okay. And so in this way, we get some object. So in this way, we can measure the probability that a string produces an outcome that starts with a given string. And so this was plan of Solomonoff. Let us take V, which is a probabilistic Turing machine. I will just machine. I will give details soon after I tell the idea. Probabilistic Turing machine. And then he says, let us define a measure for this machine, Px, defined by probability. That machine prints out, so the result on the input starts with x and maybe prints some more on the printer. So here he defines something. This is called a semi-measure. Okay, what is semi-measure? It's kind of like a measure, but there. So what mathematically is called pre-measure. So we look at basic open sets, and they are defined by strings. So our basic events are printing an initial segment of a sequence. And so the definition of a measure, here we have inequality, and we get a familiar object. But our machine can get stuck sometimes. So it can in an infinite loop and stop printing. So if we apply this thing, we don't get a measure, but we get a semi-measure. But okay, we don't need to know all this to formulate Solomonoff's prediction strategy. So he says that we should predict our prediction for bit n plus 1 if we receive first n bits, and should be the maximum value of this measure for the extension. So it should be argmax of dv x1 till xn, and then the bit x hat. So argmax of x hat. Okay, so is this prediction strategy clear? So it will compute two probabilities. It will it will look to the continuation. So let's say that all our symbols, they are bits, 0 or 1. It will look to an extension with 0. It will look to an extension with 1. And it will look what is most likely for machine. What has highest probability. So this is Solomonoff induction. This is so when you use it for extending sequence. So it's a great idea. But now this question, which machine should we use? Because it's kind of arbitrary. If we change the machine, it changes things. Yes. There exists a machine, so he says there exists a machine that makes us measure maximal up to constant factor. So this is the idea, and we can take any such machine. This is the plan. Okay, now I need to do two things. First, I should prove that there exists such a machine that makes a measure maximal, and then I should convince you it's a very good strategy. So this is paper from 1960 by Solomonoff. Everyone agrees it's the beginning of algorithmic information theory. Even Kolmogorov agrees with this. Okay, so now you think I'm crazy. Why should I care about random machine? But also another question. It's very impractical to do this. Because how can we compute such a probability? We need to use the random machine many times to estimate this distribution, but this probability, typically it's very small, can be exponentially small, so we need to run exponentially many times to get a good estimate. Or we can look inside the machine and try all randomness. Brute force, again, exponentially slow. So, useless. Okay, we have some people from company, and let me warn you, all theory, not directly, all useless, no direct use. Okay, and so I do think that it should be taught in university, maybe in machine learning, but why? Okay, and so once I listened to the radio, I don't know if it's true, but person says that once, long time ago, teenagers were lost on the ocean on the boat. They ended in an island. They stayed a few days. They were very hungry, and they had a crazy guy that says that look, on the island is a mountain. You should go there, and it will be full of food on the top of the mountain. And he managed to convince some people to go with him on the mountain. And of course, there was no food. But they were on the mountain, they had nice overview. Mountain allows to understand what's on the island. They found abandoned farm, there were no people, just abandoned farm. And thanks to going on the mountain, they discovered a nice farm. So Kolmogorov complexity is the same. So we have crazy people in the field, various gradations of craziness. And so we can look to this theory. We will not find anything useful. However, it has happened several times. Oh, did I do something? Okay, but what happens is that it gives it can connect theories. It gives a little bit structure to our knowledge. And we can discover things we should have discovered long time ago if we were clever, if we just use a brain. And so it happened several times, and I will give examples about this. It happens for normalized information distance. And I also have a bit of work like this, applied work. Okay, that's for later. Okay, so now let's go to our plan. So I told you what is this strange idea. So we have two tasks. Let me think what should be done first. Okay, let's first explain why having a large measure is good. Okay, so what is happening when people train neural network, for example, they want to find parameters. They tune parameters you can understand as maximum likelihood problem. So you can define, say, a thing that there is Gaussian distribution on the outcome around the correct estimate, and that you want maximum likelihood, and the bias comes from weight and so on. It's like all theory of neural networks. And then some people use Bayesian optimization. If there are too many parameters, over-parameterized, people use Bayesian techniques to kind of have a reasonable trade-off. But each time the team is find a probability measure that make your observed training data have large probability. And this is a good idea. So for example, imagine that we look at next bit prediction problem. So if I use, instead of a measure, the special measure, just any measure, any semi-measure. Okay, so what I'm doing is, so I apply the strategy just for any measure P. So let's do Solomonoff prediction, but we have some computable measure. And then I claim that small lemma, number of errors, is logarithm of 1 over the probability of the string we have seen so far. So lemma, number of mistakes, when we have some string W, is bounded by so the probability 1 over P of W. So if we have a measure P here. Okay, so somebody can tell me how I can prove this lemma. So note that we have a measure. P is a measure. So what we know about P is this and this. So we will predict the extension. It's most likely according to our measure P. Measure map strings to probabilities, a number between 0 and 1. Okay, why is number of mistakes bounded by 1 over P of W? Why does it happen? We don't know much about P except that these two things hold. Okay, it's very silent here. So you should stay awake, otherwise it's going to be 90 minutes of torture. You know that we're still here on the first item.
Okay.
Yeah. Okay, so you need to look at this thing here. What do we predict? We do predict extension that is most likely. So when we make a mistake, it means correct the bit we receive as the least likely one. So we see that probability after making the string longer decreases by at least 1/2. So each time we make a mistake, probability decreases, and we start with probability 1. So here, okay, I forgot to say I use binary logarithm. Okay, and so now it should be clear, right? Okay. So this is a reason, like if we want to do good prediction, we want a model that is large. And therefore Solomonoff wants a measure that is as large as possible. Therefore he chooses a machine that is larger. There is a second reason, a more convincing reason, why you want your measure to be large. It has to do with gambling. So imagine that there is expert, and expert believes that string infinite sequence is generated according to measure P. But you believe that it's generated according to measure Q that's different. Okay, even semi-measure. So P measure. So this is opponent. And me, I believe that sequence is generated according to Q. Okay, then we can do a gamble on some bit sequence, on some string. We will gamble. We will propose opponent. I will pay opponent €1 and then tell him you should pay me this ratio if we see string X. Okay? An opponent who believes in P, he will agree with this, because if we take expected value over P for infinite sequence, or just let's say for some finite sequence of given length, and so let's agree we play for n steps, then opponent will agree with this gamble. If we have semi-measure Q, if strict semi-measure, he will be very happy to do this because he expects to win. But Okay, so how do we compute this? So we take, we replace expectation by sum, x, and we sum over all x of length n. Yes? So this is expected value. Our opponent thinks he will pay us this amount. And since sum over all, so this cancels, and sum over all x will be equal, oh sorry, what did I write here? Of course 1. Correct? And sum over all x will be bounded by 1. And maybe strictly less than 1. So he will agree. But if we are right, then it can happen that the q expected value of this ratio is much bigger than 1. So if we are right, then we are gaining money. So the bigger we can make our measure, the more money we get. So I think companies must like this. Okay. Yes. So that's Solomonoff's idea. Let's make the measure as big as we can, but it still has to be somehow computable. He thinks that I don't care about running time, but at least I need to have algorithm that somehow converges. Okay, let's try. Okay, so now I need to say that this measure so there are certain optimality principles, but first let us prove that there is a machine that makes this measure maximal. So now I return to this definition. Let us try to believe that there is a measure that makes the machine that makes this maximal. But I didn't say the details of the machine yet. So let us...
what do you mean by machine making the measure maximum? So defining the maximum?
Yeah. So I claim, so Solomonoff theorem, which is start of algorithmic information theory, says there is special machine. What it means to be maximal. Yeah. Okay. Let us say a question. So the theorem. So there exists a machine, we will call it U, because in papers it says universal machine. Such that. And then for every machine V, there exists a constant CV, such that for all x, PU of x is bigger than PV of x divided by this constant CV. So this is our theorem. So it's largest, but up to a constant factor. Okay, now let's try to do proof. So I will be a bit more specific about the machine. So it will be Turing machine. It is a device that has states. So it has an input tape and a work tape. And the input tape contains the randomness. It will take an infinite sequence uniformly randomly generated. So omega will be written here. First bit, second bit, and so on. This is a work tape. This is input tape. And so there is a read-write head. So Turing machines, they are devices with read-write heads. And they scan symbol in the cell of the tape. They modify it and then make a movement, step right or step left. So it's the local computation, and here must be a finite list of instructions, what to do when you read things. Okay, and also there is printer. So it starts to print things on some paper. And here appears output. Okay, so now I will construct a universal machine. And it will try the following. It will look at a random sequence and will try to interpret the beginning as a self-delimiting program. Self-delimiting means that program tells where it stops. And what comes, okay, I'm slightly fast here, but let's not worry about certain details. So there is self-delimiting program. That means that a machine can read this program and know where it ends, and then it will interpret the randomness that comes after as, okay, so it will interpret this as a description of another machine. That's the plan. And so we need to do something for every machine V, for every probabilistic machine V. And so what's our plan? We will encode V as a list of instructions in a program. And then the universal machine will look at the beginning of randomness, see the instructions of machine V, and then simulate machine V on the randomness that comes next. And this machine satisfies conditions. So what is constant here? CV. Constant is 2 to the power of the length of this program that of this machine. Okay, everyone says yes, it's really cool. It's yeah, it makes sense. Oh, I like this. Okay, and now let's go to a theorem of Solomonoff.
So that theorem was essentially the Kolmogorov theorem and Solomonoff theorem, and everyone's.
Yeah, so independently, Solomonoff and Kolmogorov did this using Kolmogorov complexity, which is 4.3. And okay. So now let us say a little bit more. I claim that for every computable measure, such an inequality also holds. And this is easy to prove, because if we have a computable measure, we can create a sampler that generates outputs according to this measure. So we have this to be true too. Okay, so but there is one problem. The Solomonoff measure, it's not computable. It is only lower semi-computable. It means that you can approximate this measure from below, but yeah, not from above, only from below. So you can have a program that, and it's clear how to approximate, because you just brute force over all randomness and check the output. So you can have an algorithm that approximates this measure, but at each moment gives a value, and then later updates the value, but always bigger. And there is a nice property. The sampler property also works for lower semi-computable semi-measures. So we can say that this measure, the Solomonoff measure, actually I should point here, this measure. So it is lower semi-computable and the largest among the lower semi-computable ones. So this is the theoretical. So this is why Solomonoff introduced a special letter for this measure and plays a central role in theory. Okay, and now there was Solomonoff was interested in not computing extensions, but also estimating conditional probability after seeing certain measure. So let's write down. And he said that if you use Solomonoff measure n as prior, you can and you sample from a measure, conditional probabilities will converge to each other. So there is one prior that can converge to all computable measures. So let's check about this. So let's write down this statement. So the theorem by Solomonoff in 1978 says, let us look to the sum over n of expected value of conditional measure. So on one hand we have Solomonoff measure, x1 till xn, and xn plus 1. And we will look to conditional measures, so the ratio of the measures. And on the other hand, we have a measure b, x1 till xn plus 1, the same thing, conditional measure. So we will sum over n for infinite, so we will look at infinite sequence and take the measure according to p. So we will sample x according to p. And this is bounded by Kolmogorov complexity of the measure of P plus O of 1. Okay, you don't know what is Kolmogorov complexity. It's just shortest program that computes this measure. But it must be self-delimiting program. Okay. And so it says that if here is conditional measure for Solomonoff prior, here is any computable measure. And so as you receive more and more bits, your prediction, so your predicted probability for next bit will converge to a probability of opponent. Okay, so this is how you can understand this theorem. So opponent has secret information. So he can approximate in an experiment, he can compute conditional probability better. We don't have this information, so we use Solomonoff prior.
So could you be a bit more detailed about who is opponent, who is not opponent? So what is the game here? So
okay.
One is trying to predict the probability, and the other one is trying to spoil this prediction.
So we will observe infinite sequence. We don't know where it comes from.
Right.
And opponent has access to a model P. Mm-hmm. He has access to finite information about this infinite sequence we will observe. And so opponent will agree that if we use Solomonoff measure for prediction, that we will quite quickly converge to his probabilities. So after a certain time, we will both agree on the same conditional probabilities. And this is an important question, because in all machine learning papers, there are terrible probability distributions over inputs. These inputs can be huge things like pictures, megabytes, even movies, hundreds of megabytes. What means a distribution over megabytes? What does it mean? Like, okay, it's a philosophical question. You cannot have frequencies. Then you need 2 to the power, blah, 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 megabyte, yeah, millions. So, but thanks to Solomonoff, you can define probability. So there was time in the 70s, there was agreement under AI specialists, most AI specialists, we don't need probabilities. And so Solomonoff thought it was a nightmare, and he was hard working to change the situation. Okay, I talked way too much, I guess, about Solomonoff next, so we are finished with this part. But what about time?
You used 30 minutes, so
okay.
Roughly 1 hour.
Okay, that means 50% faster.
Don't try to be faster. So that would be the right advice. So.
Yeah. Okay, I think the next topic is a bit shorter. Reinforcement learning. So, what is problem here? So now there is direct extension given by Marcus Hutter to solve a general problem, not sequence prediction, but you have an agent that goes in an environment and wants to pick up as many rewards as possible. And rewards can reappear. And this is a very general system that includes games, but also sequence prediction, of course. Okay, so let's speak a little bit about how to formalize this model. And I will state the model, say what are optimal strategies, and then say that if optimal strategy exists, okay, we need to be a bit more specific now with what environments we allow. I will say in what sense I consider this means, and then I will say optimality theorem. So if there exists a good agent, it will be then also the agent based on Solomonoff prediction works equally well in some sense. Okay, so first, what is the model? So we will view environment as Turing machine. And agent is also a Turing machine. So there are two machines called agent and environment. Okay. So by the way, after this topic, I will take a break for questions. I forgot to do it, but okay. So, let's make more space. So, environment, it will produce some reward and some extra observations. Reward is just some rational number. Can be any number, it doesn't need to be bounded by 1 or something, any rational number, order 2, and so on. Okay. So environment will write this down and send it to agent. So agent will receive, agent will choose action, and we write it by y1, y2, and so on. And these are one-way tapes. So once agent chooses y2, it will go to environment, and then environment will write down the third reward. So initially, agent receives reward 1 and information 1 here. Then it will write down y1. Agent chooses action. For example, take this money, or take eat this, or charge your batteries.
So these y's are bounded in some way, or they can grow infinitely.
Yeah. So these tapes, they move only to the left, both tapes. And each time, so there are rounds, and each round,
each individual item y1.
yeah.
Is it like a big string, or is it a small string, or is it just a big? What is it?
Okay, for this talk, let's say a string of fixed length.
Or fixed length.
Yeah. Okay. So let's keep things finite, not to get in trouble. Okay, so environment sends a number and another string of fixed length. And then this is just one round. Okay, so so what's the goal of agent? It's to have maximal reward. So we have, so we will have a fixed horizon. So we will play for m rounds to be fixed. Model can be generalized, and you need, in reinforcement learning, you need to do postponed rewards need to scale down, because otherwise you can have infinite postponing, and we don't do it. But okay, here we have enough symbols already. So the goal of agent is to make the sum of rewards maximal. Okay. Yes. Environment is probabilistic machine, and it has a word tape. And also, like a tape with probabilities, like we had with Solomonoff induction. But we say that agent is deterministic. Just for the talk, otherwise I have to write too much. It's not so essential. Okay. And now the goal is to make an agent that gets maximal possible reward. So what is the problem? Agent, we want to make a single agent that works optimally in all environments. So this is an ambitious goal, but it's impossible. So let us first understand why it's impossible. There can be trap. What can happen is, so know that environment depends on actions of agent. So we can have an environment that says that every reward is equal to the first action. So if he writes bits, imagine we have just single bits, and agent chooses 1, then all rewards are 1, he chooses 0, all rewards are 0. But then we can have a second environment where it is the opposite of the first action. So there are two environments, and there is no agent that gets optimal reward in both environments. So that's why our theorem will be smaller. We will consider a set of environments M, and we will say that if there is an agent that in every environment of M can pick maximal expected reward, then agent defined by Solomonoff induction will also pick maximal reward, expected reward. Okay, so now I just have to define everything I say. I will write the theorem, and that's it for reinforcement learning. So, okay. First, we need to speak about expected reward for environment. Remember that environment is probabilistic. So, Okay, so let's define this inductively. I use same notation of 2005. So let's say expected reward between rounds K and M when P is original measure. According to some protocol P. So I will, so agent P, how much agent P will get. I will use some extra notation. I will say that, here I will say that, oops, ZT is equal to the triple RT OT. So the reward X observations and the action YT. So for better notation.
So the probability P is in the environment, right? So,
Yeah.
So that's essentially the bits that are on the tape.
Yeah.
Okay.
So most references I cite here are in the announcement of the talk. So there are 6 references. They're the most important. Okay. So if we have agent P, environment P, P is a measure, then the reward after we receive Z1 of ZK. So expected reward is expectation over P of the reward at, oh sorry, K minus 1 should be here. The reward at step K plus, and its recursive definition. Sorry, we need to choose the best action of it. I forgot to write the maximum here. So, expected reward of the best action. So here our action is yk. And then we have expected value of the reward of k plus, and then the recursive definition p, k plus 1 till m of z1 till zk. Okay, this formula, is it clear? So it's big formula. So for some it's clear.
It's like planning actions.
Yeah, planning actions. There is one thing missing, that's the base of the reduction. So I need to say that v k of v m plus 1m is equal to 0. So now we have the base of recursion. So this is reward. It's optimal reward you can get. And so when we look to, so the best policy, you can say P of P, define the best policy as the one that chooses this reward. So again, this is a disaster to compute. If we unfold recursion, we have to look at the full tree. So this is theoretical notion, but okay, we are in theory land now. And there is actually some claims about logic in Hetter's book. Okay, it's for later. I'm already confused enough.
So far we claim that this recursion defines the optimal...
It defines the reward of a fixed strategy.
Of a fixed strategy, okay.
Yes, but we can use it. Sorry, for optimal strategy, you're right. Oh, okay, now I mix. Sorry. I was stupid. So we don't have max because the action follows from the given protocol. I'm really sorry. So
For the given protocol, that defines the reward for the given protocol.
Yeah. So we get so we have like k is equal to the protocol of x1, z1, zk, and the next environment action. So t minus 1, rk, ok. So this goes into this z key here. Okay, but now we can also define the optimal one, and then I place the max back. So this is optimal reward. Okay. And so here optimal protocol chooses this maximum. over yk. So now we have now we know what it is optimal reward, and
But we cannot compute it.
yeah, we can compute an exponential. If p is computed, the measure is computable, we can compute an exponential time, which is useless in practice. But we can make a proof system and try to improve it. And moreover, with help of proof system, you can compute it in best possible provable time. So this is...
And what do you mean by a proof system?
Okay, any of this business that you have with elementary arithmetic and deduction rules, and then we believe it's consistent, this proof system, and then we can...
So how...
But it's a little bit tricky. Let's first go to the statement and then quickly discuss this idea of speeding up things. To be honest, I didn't understand it from the book. I was hurrying to get this right by the start, but...
And by the book, which book you mean?
Hutter book 2005, and I failed to read the new one that's appeared just a few days ago. Yeah, and it says that it's easier to read the new one, but it's also longer, twice as long. Yeah. Okay, let's. Okay, I just write down the statement and then we're finished. Okay, so imagine there exist policies P1 till Pn. So these are policies that have increasing horizons. Now that we fixed a horizon m here, so I forgot to write.
Fix m.
Yeah, in the left. Fix m. So now for increasing m, we have different policies, and assume that for every model, for every environment in our set of models, the policies approach maximum possible policy. So we will have that the reward of pi, pm, divided by m, so it is the rate of reward we consider here, approaches to optimal rate of reward. Sorry, and here we have the policy, here we go from 1 to m. Okay, it's not readable. Let me write it again. Okay. So we have definition of reward. So for all m, so we have policy E, and the policy is Pm. We have probability environment P. We start from 1, we go till m, and we divide by m here. And we assume that this approaches the best policy, P1m, divided by m. Then, if we consider agent based on Solomonoff prior, it will also satisfy this result. But now we have fixed agent. So if there exists fixed agent that approximately works well, then we have specific agent that also works well in all environments. So that I just have to copy it again. And now I will say P, there is a special psi measure, so we need to modify Solomonoff's prior a little bit. I will explain it in a second. And this will approach V star 1m. Okay, just the same thing. 1m. Okay, so one thing is left to do. I need to say how it works in this. What is measure psi, the modified Solomonoff prior, and how it works. Okay, psi, I will use the simplest definition I found. 2 to the minus Kolmogorov complexity of P of x, where we take the sum over all measures in the language. So here is prefix-free Kolmogorov complexity. They define coefficients that sum up to 1. So we have that psi is a semi-measure. Sum up to at most 1, sorry. So this is not a measure, it's a semi-measure. Okay, there are some computability issues. You can modify this definition so that it becomes lower semi-computable. So it just, okay. Let me say that we will use something that satisfies this, because I'm cheating. Okay.
Okay, so so that's simple.
Yeah.
So the limit is with m going to infinity.
Yeah, sorry.
Now the expression on the right, so this we start. It also depends on m, as you put it. Is it?
Yeah, the policies depend on m.
What is v star? V star. So what is a little bit? It looks a little bit strange. Needs explanation. Why is something depending on m tends to something else depending on m? In your so.
Yeah, so if we can increase m, possible reward may increase. So, okay, yeah, you mean if this is infinite, it's poorly defined. Is this a complaint?
No. The complaint is that when we usually think about limits, there is a function of m, which with m going to infinity approaches a certain limit.
Yeah.
And this limit is fixed. M is variable, right?
Yeah.
Oh, here.
Yeah, so this, yeah, okay, I see, it doesn't make sense. Yeah. Okay, in what sense does it approach? Okay, so if this has a limit, then this has the same limit.
Maybe the difference between the two tends to 0.
Yeah, so let me write it better. Limit m, limit m. So that's how it's written in the book, so I had to remember about the proof. Thank you for question. So if limit exists, they're finite, both finite, and yeah, thanks. Okay. Yes. And now I've done everything. No, I didn't say how the agent operates. Okay, so agent doesn't now measure p. We'll just replace p by this strange measure xi. And unfortunately, I don't remember I do know definition is difficult. I do know one definition that's not in the book, but one definition that makes the proof work. But I will not say what it is. Okay, so so you can use something very incomputable. If you use this as definition, proof works. You can use any measure, any mixture of all the measures in model P, and proof will be correct. However, there is a time-bounded version in the book, so that was questioned. So what can we do? And there it's important that measure is lower semi-computable. And to be honest, I didn't have enough time to read the book on this book Hutter 2005. I didn't have enough time to carefully read chapter 7. And so I don't understand the proof, but as I understand, it's important that psi is lower semi-computable. So I'm not sure if his proof is working with the definition he gives. But it's fixable. It's nothing serious.
Could you perhaps say a couple of words? What is K of P? Because not everyone...
It's shortest self-delimiting program that computes measure P. So P has to be measures here. So we only consider measures in M. Okay. Yes, so short 2 minutes about time-bounded results. So I will just say the statement. So once we have fixed xi, an approximation of xi, so there is a time-bounded variant, and there is some claim in the spirit of all environments. So IXC measure xi with time-bound t considers only environments computable in t time steps, and with some 2 to the power L extra time times t, so the time plus something smaller than this, he can make a time-bounded measure that can read all environments that are computable in time t, have a description of length L bits, so Kolmogorov complexity at most L bits. Yeah, run in time t, I already said. Okay, and the optimal policy is an optimal policy that's provable in some sense. So where you can, so it's about environments where an optimal policy exists, but also a proof exists where this policy is optimal. This is the same. But I'm really sorry I didn't get the time through this chapter for the details. And the idea, this I do understand, but I have no time now. Idea is to have a program that can beat all programs that are that can be fast, almost as fast as every program that has a provable runtime bound. So fast I means the runtime, the proof of the runtime. So that has the best provable runtime and is provably correct. So he plays with kind of proof systems, and then.
So in his book, he also considers this provable runtime bounds and things like that. So that's that's in his book. Okay.
Yeah, this is chapter 7 in 2005 book. It's also in the recent book. And here,
if you replace provable by, let's say, computable and polynomial time, so what changes there? So my vague understanding of Kolmogorov complexity is that it doesn't really work as nicely if you consider some such class.
Well, okay, we need to be careful polynomial in what? So there are several parameters, there is a time, there is a description. And so I assume you take L fixed, and then t you replace by some polynomial. And okay, then then the proof will this bound will be valid. But here is a term that's needed to, the time bound is itself a function, so you need also to evaluate this function. This is inside here, but also there is a huge linear coefficient that corresponds to finding the proof that it works. So the agent will use a fraction of its time to iterate through proofs. And if we believe that the time bound has not too long a proof, so we can say that optimal time bound for an environment might be bounded by a constant. And so if we can beat all the constants in this model, then we will find this. But it's completely insane, not useful. But there is some claim of optimal time-bounded situation, the time-bounded agent. Okay, so this is all about Solomonoff induction. We didn't speak about Kolmogorov complexity yet. Yeah.
Can I interpret this theorem that a successful agent fully models environment? So, in the sense that it has Solomonoff induction that really predicts what will be the output of the environment.
Yeah. So, indeed, this is the main idea. Let's try to model also the inputs, while other reinforcement learning systems do not do this. I mean, not explicitly, it's more about mapping from inputs to rewards. So they aim at doing this. But, okay, you need to... actually, I should not give such answers. I know nothing about reinforcement learning, but at least that's what the book says, that there is more emphasis on modeling the input in this. That it's like an unsupervised component inside this model. Okay, and... But I mean, it's like really necessary here because we take expectation over future inputs, and so it's very strange that other model. Okay, let's not speak about things I don't know. Yeah. Okay. So now we finished here, and so I'm also factor 2 too slow still. So what's the time now?
Yeah, you used another 30 minutes. So.
Okay, I will say what's Kolmogorov complexity. I will skip this thing because I think I should speak about this thing and about neural. This is very short, it's less than 10 minutes, I expect. But this I want to speak about, and only 30 minutes left for these 2 points. Okay. Also need some space. Okay, so finally, definition of Kolmogorov complexity of a string X. So we will use a Turing machine. So the goal of Kolmogorov complexity is to quantify how much information there is in the string. So why do we now care about this? There is actually a nice relation with Solomonoff induction. So we can think about mxy and m of x. We want to understand the bias of Solomonoff induction. And this is very roughly equal to 2 to the minus conditional complexity of y given x. Amount of information inside y given x. So Solomonoff induction has a preference for very simple models. And so this Kolmogorov understood that his definition and Solomonoff were closely related. Okay, so we have a Turing machine, and we use it to map strings to strings now. So there just has one word tape, it has a program, it evaluates the program, and then the string should, the output should exactly be x, and the machine needs to half. So that's why I say Turing machine maps strings to strings, bit strings to bit strings. So, C of x is mean of the length of v, so that u of v equals x. I guess everyone, so, okay, it's new for some people. So, Turing machine can be your favorite computer programming language. So, shortest length of your programming language that brings a string. Or it can be like a zip program or something. And so, our definition, okay, do a special lettering because it's for optimal machines, so let's have a machine V like this. Okay, so again we have the same problem. Our definition depends on machine V. We want a definition that does not depend on V, but we can have an optimal machine. How it works? Well, if your favorite language is Python, for him C++, then let's use Python compiler and C++. We can add a compiler to the program, and then the receiver can run this. But we need a self-delimiting compiler. So when we receive the concatenation of two programs, we need to be able to split it again. Okay, so this is the definition of Kolmogorov complexity. So definition of optimal machine. So here is theorem by Kolmogorov from 95. And there exists u, such that for every v, there exists a constant v for all x. Complexity v of x is the opposite. Complexity of u is smaller than complexity of v of x plus this constant c. So definition of optimal machine. When we change the machine, we change optimal machine, we change complexity by at most O of 1. So let's do a few exercises, because I think only 1/3 is awake now. And, okay. So I need some space. First question. I claim that Kolmogorov complexity of x is okay. If I have universal machine, I will fix it and drop a subscript. Kolmogorov complexity is bounded by length plus O of 1. So how can we prove this?
Because you can take the Turing machine, which just
Nothing.
write down this word and that's
Yeah. So it receives program and just stops, and that's its output. Yeah, exactly. And so in this special machine, we will have that it's exactly equal. And then we apply optimality, so we need to add O of 1 when we go to universal machine, of optimal machine, it's nowadays called. Okay, next, complexity of xx is smaller than complexity of x. What do I mean? Just concatenation of strings with itself. Is smaller plus O of 1. It's clear, right? What machine we consider? Just a machine that gets a program, computes the output, and then copies again. Okay, what else should I? If we have computable function, C f of x is smaller than C of x plus O of 1. It's also clear, right? So we have a computable function mapping strings to strings. Do it a bit higher. So this is okay. So let's have a string only containing zeros. We have n zeros here. This is bounded by log n plus O of 1. So we receive a number in binary. So we consider the machine that interprets program as number in binary and then prints this many zeros. And then by automatic. Oh, it's too easy for you. Okay, now next question. I claim that most strings have Kolmogorov complexity at least n. Where n is the length of the string. So let's fix n. So 1 minus 2 to the power minus c fraction of strings. So for all n, c of x bigger than n minus c. So if I choose n large, most strings have this complexity. So why is it true?
Because there are not so many simple strings.
Yeah, so let's look to the definition. Machine that matches bit strings to bit strings. Number of bit strings of length at most k is to at most, so one string of length 0 plus 2 plus 4 plus. So number of strings less than k. Of length less than k is 2 to the power k minus 1, 2 to the power k minus 1. And here we are interested in strings of length less than n minus c. And so this is 2 to the minus c fraction of strings. Okay, I wanted a difficult exercise so I could clean the board, but I failed. So you replied right away, which is very good. Okay. So let's now say why Kolmogorov complexity is not computable. And this is because of Berry's paradox. So consider the smallest string that has no description in less than 13 words. 20 words. Yeah. Okay. So this is contradiction. And okay, somebody forgot to switch off microphone. Yes. So let's now prove it. Why Kolmogorov complexity is not computable. Because it's too long that we saw proof. So, x to c of x is not computable. Okay, we will implement Berry's paradox. Smallest number that has no description in less than k bit. So it is equal to minimum n, for which c of n is larger than k. Okay, how can we define Kolmogorov complexity of number? C of n is equal to c of just string of n zeros. Okay. Yes. So by definition, we have c of nk. It is larger than k. That's just definition. No issues. Now let us assume that Kolmogorov complexity is computable. Then the mapping k to n of k is computable. Okay, so we have this rule for computable functions. So we can bound by complexity of argument. K plus of 1. Of 1 is the length Kolmogorov complexity of the function, actually. So here is that. Okay, and then this is bounded by log of k. It's also somewhere on the board. Okay, so if k is large, then we have contradiction. So our assumption must be false. Kolmogorov complexity is not computable. Also means Solomonoff complexity is not computable. We didn't connect the two yet, but it's kind of easy. So why is m of x m of x is bigger than 2 to the minus prefix 3 Kolmogorov complexity. This is just Kolmogorov complexity on a machine in which all valid programs form a prefix 3 set. Okay, so why is this true? Well, look, remember definition of Solomonoff probability, it guesses a random program. Well, it can interpret this program as a program on prefix 3 machine and run this program. So here we need prefix 3 machine. So Solomonoff prediction is like this. Okay. Yeah, but I should stop about Solomonoff prediction because I need to go to some applications since we have applied people now. So so I skip this and let's speak about like 1 or 20 years ago. Yeah, 21 years ago maybe. Vitami was interested in a problem that could be called, so now people are interested in IT alignment. So there are pictures, there is text. How can we make connection if we not give an explicit connection? So there was a talk by Ilya Sutskever viewed by 100,000 people. So it was sent to me, this movie. So a talk about Kolmogorov complexity. It's unprecedented. So and I didn't know about this. And then he speaks about alignment. But actually this problem was considered by Vitani in kind of easier variant. He wanted to translate words. So he had, so it was beginning of internet, beginning of, at least for me, beginning of Google. It existed, or Yandex existed 10 years or something. Okay, and what's the, yeah. Okay, let's go to the problem because I should hurry. So what they say that there is a bunch of words in Spanish. Here are a bunch of words and English. But the translation does not correspond. So there are 100 words in Spanish, 100 in English. We want to have a matching for the same meaning. It is a problem he considered in 2004 Google information distance. And so he solved this problem just by looking at hits from Google. And the technique he used was an ID from information distance. It's a very simple technique, I will say later, but it just to keep machine learning people awake, I already tell application now. Okay, so yes. So now, what is information distance? We can define Kolmogorov complexity, conditional Kolmogorov complexity. And I will define it on an optimal Turing, optimal prefix-free Turing machine. So now it's very easy. Turing machine can read the string y as exahel, and it needs to print x, and so the minimum is over program length, of course. So minimal program that can take advantage of y and prints x. And now I switch to prefix-free Turing machine. All programs form a prefix-free set. All halting programs. Okay, so we have k of x given x is smaller than O of 1. Program just copies the helper string to the output. Okay. Yes. Vitani wanted to define a symmetric measure that corresponds to the distance between x and y. If x and y are very different, the distance is large. And so, natural definition would be, look at a program that maps x to y and y to x. So, the distance you can find as x and y is minimum of length of program such that up x equals y and upy equals x. Okay, and then he proved it's optimal in various senses, like the smallest distance that does not put everything to 1, so that is at least large for a reasonable number of strings. And then he proved nice characterization. This is equal to maximum of kx given y and ky given x. Okay. And this is very good news. Okay, so here is a logarithmic term, and I've made some work that under a few assumptions you can have O of 1 here. It used to be O of log d before this. And this has to do with prefix-free machines. If you're on a plain machine, always O of 1. But then you don't have triangle inequality. So that's why I switched to prefix-free machines. Okay, so now there is this information distance. So this is definition.
So it's called information distance.
Yeah, this is information distance. So it satisfies all properties of almost all properties of information distance. So if the strings x and y are the same, then it's bounded by a constant. I mean up to O of 1 terms. Then it's bounded by a constant. Okay, uniqueness, unfortunately, it can happen if x is very similar to y, then it's still below some constant. Then it's symmetric, triangle inequality. Okay, it's a bit annoying. I will not write down, it's also satisfied when we use prefix-free machine. Okay, that's it. Now there is a small problem. How can we approximate this in practice? Because what's the plan? Let's use compression algorithms like zip or whatever algorithm. But they don't have auxiliary tape. They're very poor on this. And there he will use very important theorem which is called symmetry of information. If we have a pair x and y, then prefix complexity equals information in x plus y given x and Kolmogorov complexity of x plus O of 1. So this is symmetry of information. It's one of the very important properties of Kolmogorov complexity. So what does it allow to do us? So we can have conditional, so in practice we approximate, we draw this term. It's just a number bounded by a little bit more than n because it's prefix-free complexity. It's n plus 2 log n. But it doesn't matter if we drop it, we have here the term order log length of x and y, or complexity of x and y. So this is a small crime. And so conditional complexity we can get as the difference of complexity and complexity of pair. So what he does is he runs zip, but on concatenation of x and y, and then runs zip on complexity of x. So he gets conditional complexity, he takes the maximum, and he has approximation of information distance. So that's the plan. So, but information distance is a bit annoying because to solve this problem, some words are, he needs a normalized notion of information distance. And this is very easy. He will just divide by the maximum of Kolmogorov complexity of x and y. So let us say what is the variant of normalized information distance we will use in applications. So we will have kx minus the minimum of kx, ky, divided by maximum of kx, ky. So this is a number that's approximately between 0 and 1 if objects are complex enough. Okay, and now we understand how we can approximate this using z distance. Okay, but how does it connect to our problem with matching strings in two languages? Only using Google hits. Okay, we need one more very important program is MDL bound of Kolmogorov complexity. So we can say that for every computable measure, okay, here I have a discrete measure. So here I mean that sum over p of x is bounded by 1 for all strings. So it's a discrete, not continuous measure. It is equal to k over p minus log over p of x plus of 1. Or it is a bit confusing, let us say 1 over p of x. So there is a whole business about approximating Kolmogorov complexity using such approximations. It's called MDL by invented MDL, minimum description length principle by Rissan, and there is a recent book by Grunwald. So we have computable measure.
Logarithm 1 over p.
Yeah, 1 over p. And this is just one of the famous encoding schemes like Huffman encoding or arithmetic coding. It's well known. Okay. So, what's the plan to solve this problem? Let us say we know everything, all frequencies from the internet. Let's use frequencies from the internet. So let's define a probability measured over words. Tokens are words now from the internet. And let us measure this as the Google hits of x divided by w. W is sum of all Google hits. So all the things we have. Okay, we want to compress x. If we take internet for granted, then we get our p from the internet. So we will drop this term and just approximate Kolmogorov complexity given the internet using this probability. Now we can also approximate internet hits of pairs. It's very easy. Just Google hits divided by xy. And he uses same normalization constant. Okay, it's not mathematically accurate, but okay, it might be not so different. So this is d of xy. Okay, and now we can evaluate normalized information distance. Since he uses the same normalization here, it disappears in the denominator. Right? So we have ratio of logarithm of ratio. So this will be minus logarithm will appear here. Here we will have plus logarithm w. So log w will go out here. And so we will just have logarithm of opposite. Okay. Google hits of x and y plus logarithm plus maximum plus minimum. It's minimum, right? Yeah. About 1 over p. So we maximum of log Google hits x and Google hits of y. Okay. Sorry, I'm creating a mess, but you can replace it yourself, I guess. So here we have maximum of, and again, Google logarithm of Google hits like this. So just fill in approximate Kolmogorov complexity by Google hits. And we have a normalized information distance, a number between 0 and 1 that says how related are the words. And so then he takes some anchor words and then uses normalized information distance as word embedding. So this is a bit difficult. It's clear, a vector of real numbers that represents a word. And if words have same meaning, then they will correlate in the same way with the anchor words. Here he uses anchor words, a few words for which he knows translation. So, okay, I didn't say it. He's given a small dictionary of anchor words, and then he needs to find translation of new words, using all internet for unsupervised learning.
And that was from Susket.
Vitali and Celebrasi.
Consider already this.
Yeah, in 2004 he has this algorithm.
Already with Google Hits.
Yeah, with Google everything. Well, there is 2003 paper about information. Well, 1999 is information distance. This theoretical paper, Vitani, Zurek, Gach, and one more. Then 2003 is paper about normalized information distance with approximation using zip. And there he makes classification of music files just using this technique. Approximate Kolmogorov complexity using zip. And just many, like genome classification, protein classification, and so on. And this was 2004, I think, this paper, a bit later.
And so I suppose that in practice it works, right? So it's with Spanish and English words.
Yeah. So he had a bunch of applications. At the time, it was better than things based on other information distance. But then people started to think, oh, let's think what is it? It's just a very good way to approximate frequencies using some tree. So people improved the distances. And quickly it was no longer the best. And this is what I mean with mountain. So Vitani went on the mountain, useless thing, but he know where people were missing something. And so he had, it was very famous. And there is a paper of me and Attila Farkas in 2018 where we noticed a similar thing. So there was specific type of genome classification problem. People were designing SVM kernel. And we used the zip to create a kernel that satisfy properties of positive semi-definiteness. And then applied it. It was not better. It was like about equally good on a lot of data sets. But our measure did not use any domain-specific information. So other measures were like carefully designed using knowledge from biology. So that's it. So now let's go to the plan. So we are almost finished. Only this thing I should speak about. So what about time?
At this point we are negotiating about time.
I need less than 10 minutes. 5 is okay.
Okay,
Yeah.
I take it 15 minutes.
With the factor, okay. Yeah. Okay, so I watched this movie of Ilya Sutskever. And he says that neural network can be used for sequential prediction, so estimate probability of next bit, and it is a good universal approximator. There was the claim. And after the talk, he was attacked for this. Okay, and he says that he agreed that it's all very speculative. And so I've been reading last year, I've been reading a book by Robert Daniel Roberts and Yoshida that studies very large neural networks. And so turned out that neural networks, according to the theory of this book, neural networks are not performing general computation. So its main conclusion. So okay, what might be why neural nets? So nowadays there is a strange situation. Neural nets have many more parameters than the input data. And all theory of generalization breaks down. So, but there exists something like a neural tangent kernel. If the net is very shallow, but very wide, so not deep, whatever, 20 layers, but billions of parameters wide, then its solution can be obtained from linear regression. It's theory of neural tangent kernel. Robert, but everyone agrees that if neural network does something intelligent, it must be a very deep neural network. Because then when you go to the next layer, each time something nonlinear happens. Okay. So, why might it happen that neural network, when you train it with gradient descent, it's not overgeneralizing, not simply remembering the data set? So there exists a theory that says if a hypothesis is simple, so all the Solomonoff induction says you should have bias towards simple prediction. So if a hypothesis is simple, then you can encode it in the weights in many symmetric ways. So a neural network has a huge number of symmetries. But the simpler is your hypothesis, the more different ways you have to encode it. And so people think that maybe therefore it might do something intelligent. And this idea was made stronger when people discovered lazy training. They noticed in very wide network, the distance, the updates of the weights is very small. So you generate random weights, and then you run gradient descent. It's only a small change of the weights compared to their initial size. So it looks like gradient descent picks a random solution. And since simple solutions have much more symmetries, they are much more likely to be picked. So it's kind of naive idea. And so, thanks to the results of book of Robert Daniels, we can say something what happens if a network is ridiculously large. So, it turns out that in this case, network is just interpolator. It fits cubic polynomial to the output. So, but I need to say in which sense it's cubic polynomial. So this is the last part. So we have a training set. So we have a training set x1, y1, a labeled training set, and we consider regression here. So y is a real number. And so we have xn, yn. And now we fix the test point. Neural network will make a prediction, y tilde. The claim is that if we fix all inputs, we have cubic polynomial of the training labels, y1 till yk. But the polynomial, the coefficients depend on x tilde, x1 till xk. Xn, and the size of training set. So this is claim of Robert and Daniel's book. But there are three things are happening on the neural network. It has to be ridiculously large, definitely not practical network. So claim A. First, network needs to be very deep. Depth is equal to gamma times width. Gamma is some small number, let's say 0.001. And we need to take the limit for width goes to infinity. Second, what needs to happen is critical tuning of the parameter, so there is no vanishing gradient. So you need to carefully select step size. Step size is constant except for offsets. There you need to have deeper layers, need to have smaller higher layers. Near the output you need to have smaller offset. So a critical tuning. Activation function. Not all activation functions allow critical tuning. So activation function which are allowed is ReLU and TAN-H. But for ReLU, another place in the end of their proof doesn't work. So we have TAN-H. Only TAN-H are of familiar activation function. And then there was a third one. Let me look to my paper. Oh, I already said it's a regression solution. And under these conditions, network, when it gets ridiculously big, it approaches a polynomial in y, which means that neural network, at least if it's ridiculously big, it approximates, it's more like an interpolator, so polynomial interpolation it does. And so normally in big networks they're trained to zero error. But there are some assumptions in the theory. The question is what width is right? And I read the book, but I don't get, there is one point, okay, there are many points I don't understand yet, but one I'm very worried about is invertibility of NTK. So it's guaranteed to be invertible, this matrix, this neural tangent kernel. But the best proof I know requires exponential width in the size of the training set. So I think that this width needs to be exponential. But all other parts of the proof require quartic dependence on the data set. But I think it can be improved. But still there is this issue of invertibility of NTK. Okay, so this means that there is some theoretical evidence, some very weak theoretical evidence that says that neural network can not be used as to learn general computation. So it just maybe the success is just discovery of how powerful is interpolation. Okay, so that's all our program for today. I'm finished.
Okay.
So, thank you very much.
Okay. Now time for questions.
Yes. It was a lot of information.
Yeah, it was dense, but it was nice. So,
Okay, thank you.
yeah. So, well, okay.
Yeah.
What profit could we get from your lecture?
What?
Profit.
Profit.
Yes, like
Okay.
from practical problems.
Practical profit.
Yes.
So I started by saying no practical profit. No, I can go back to this mountain. So let's think about what happened with Vitani. So there was some obvious way to understand frequencies while creating a distance that depends on the data set for SVM kernel, for example. People missed it, but Vitani, using this nice theory, it was easy for him to get some formulas based on normalized independent, test them and see it work better than existing ones. It's a very, very simple procedure. It was the same in 5 different domains. Something that was completely missed but should not have been missed. And I did the same 6 years ago. So that's the closest to practical profit.
But what connection does it have with the first topic that you had about Turing machines? Can't you write the same formula without knowledge of Turing machines?
Without knowledge of Turing machines.
Yes.
Yeah, so when you see Kolmogorov complexity, you should change it by logarithm of some probabilistic model you have fitted. And so there is MDL theory that takes this further and says, okay, if your model is very complex, you might be overfitting. So you need to encode your probabilistic model also in the description length. So count it inside the description length. And so this theory of Solomonoff was inspiration for MDL. So if you look to first paper 1978 by Risanen, he will speak about Kolmogorov complexity.
So you must go back to Kolmogorov, I guess, complexity. You can't just write this formula without it, I guess, yes?
Well, idea come from Kolmogorov complexity. In practice, you can compute it because these books and this discipline is designed to be useful in practice. I never checked overview papers, but these people still exist. So to get grant money, they need to show that somehow useful. Yeah. Well, that's what I assume. I don't know how off is machine learning the last 40 years. Okay. Yes.
Are there any works that consider the opposite limit on the neural networks, for instance, when it is very deep but not that much wide?
Yeah, so I'm not specialist in this, but I watched Suitskever movie with 100,000, and they discussed this. So there are very deep networks, and they are trained to like simulate very complex computations, but they need like curriculum learning. They speak. I don't know what it is, but I guess you start with simple examples to learn lower layers, and then increase complexity of data and train bigger layers.
So could you, in a couple of sentences, maybe sum up what was the idea of Suitskever in this talk? So
yeah, it's very similar to Vitani's idea, except with practical details. He is basically saying Kolmogorov complexity must be connected to unsupervised learning and translating results from one domain to another domain. And he says if you have probabilities over English language and a probability distribution over Spanish language, you should be, in principle, be able to make the mapping, he says. And then he makes a lot of vague claims. But then in the end, he speaks about sequential prediction, and he says that optimized neural net for sequential prediction can be used to take advantage of unseen information, and then you build your network and use this network to train on a classification task with few data. So this is, okay, to transfer learn, okay, I forgot, yeah, something, transfer learning, there are some names for this problem. Okay.
okay.
So, thank you.
You just mentioned that the deep learning is not the general computing, right?
There is theoretical evidence that if neural network is ridiculously large, that you can compute the prediction without using neural network, but it needs to be trained with stochastic gradient descent in simple form. So all the weights with basically the same learning rate, and except for offset, and this 1 and 2 conditions. So it looks like it's just making some strange computation with matrix inversion. But okay, as I said, there is this note, it's theoretical result if it's ridiculously large neural network. Okay, yeah, I hope it's answered, yeah.
I wonder why it's specifically cubic polynomial then, and not some...
It's blind.
Yeah. So it has to do with certain terms in a Taylor expansion, and there is a miracle, they become small.
Okay.
But there is no easy explanation why at some point these terms become small. And to be honest, this is, and happens in page 350 of the computation, and it's precisely this page. I don't understand precisely this point. So, but okay, I will read it again. Next time you can ask me, I can show you. Yeah.
Could you give references to all of the sources that you mentioned?
Yeah,
So,
in announcement of talk there are 6 references. They're the most important ones. I gave like 3 more or something by Risanen of MDL, but the important ones are there, and you can send me email and ask me what you want more.
okay.
Okay, we will ask the question.
Yeah.
Thanks for the lecture.
Yeah.
So, did you find some researches where, so we know nowadays neural networks can be used to compress data. And we know the data compression is connected with the notion of Shannon entropy, and it is connected with Kolmogorov complexity. So did you find some statements where some theorems were proved, like the algorithm that uses neural network to compress data is algorithmically optimal? In that sense, it reaches asymptotically Shannon entropy value.
Okay. How can we make such a statement? Okay, let me first say something general. There is a connection between Kolmogorov complexity and Shannon entropy. It's like this. So expected value of Kolmogorov complexity of x when we take x from a measure. So we have a set of strings, f is a measure on this, let's say, finite set of strings. Then this expected value is so this is equal to Shannon entropy of P plus complexity of P plus O of 1. So here is connection between Shannon entropy and Kolmogorov complexity. And you can make a lower bound because on prefix-free machine you have prefix-free code. So this must be at least Shannon entropy of P. So there is connection. So in context of neural networks, we could say if you have a large test set or something that and the network predicts probabilities, then you can estimate probability measure that says something about quality of prediction, and then you could say average. Okay, I'm sorry. Let's no. This yeah. Yeah, I don't know how to connect to neural nets to be clear. Yeah. Okay.
Okay, let's sing the speaker.
Yeah. Thank you for this long lecture.